So as I was telling today, we have as speakers the awardees of the María de Maeztu this paper award for a PhD and a fellow. These are Clàudia and Michele. And well, Clàudia will start with his presentation, with her presentation. So as you know, she's a PhD student at the Imaging Group led by Daniele, and she will be talking about the magnetic fields in hot Jupiter. So please.
Okay. So yes. Okay. So thank you. Thank you very much. Yeah. So as he mentioned, today I'm going to talk about magnetic fields in hot Jupiters. But I want to take advantage of this opportunity and let you know the updates that we have been doing after the publication of the paper. And also to talk to you about another project in which we are working in the group that tries to answer the same question as the paper, which is why hot Jupiters are inflated. So first of all, as you know, until now, there are more or less around 5,500 confirmed exoplanets. Among them, 1,600 approximately are gas giants. And inside gas giants, there is a subgroup of planets which are hot Jupiters. They have a particularity that they orbit really close to the host star. So they orbit within distances of 0.1 astronomical units. This means that the average period of translation is really short. They take on average around 3 days. And they are tidally locked, so they orbit in order that the same side of the planet faces the star orbits, basically. So as they are really close, they have high temperatures, which are above 1,000 Kelvin, and they receive a lot of irradiation from the star. If you compare Jupiter to these hot Jupiters, they receive approximately 10,000 times the irradiation that Jupiter receives from our sun. So we imagine that there might be some differences, although they are part of the same group of gas giants. But all these properties have been well studied and we know how they work. But there is one property, which is the radii, that doesn't match. What does mean that they don't match? It means that we compare the observations with the evolutionary models of hot Jupiters. We can see that the radii of the observations is higher compared to what we obtain from the model. This can be seen in this figure. In this figure, here you have the radii and here you have the equilibrium temperature of the hot Jupiters. Each dot corresponds to a hot Jupiter, and the red line is the evolution that we expect, just taking into account the irradiation that the planet receives from the star. So you can see that after 1,000, there is a slight increase in the radii, but most of these hot Jupiters are above this line. So it means that there should be an extra sort of heating that expands them and makes them have the radii that we observe. There are a lot of possibilities, but one of the most promising is ohmic dissipation, and is the one that we are studying in our group. So basically, ohmic dissipation can be found at the atmospheric level, but also in the dynamo region. At atmospheric level, we have in the atmosphere basically charged particles, and there are strong winds due to this contrast of temperature in the day side and in the night side. So these winds with charged particles generate currents, no? So these currents combined with strong magnetic fields typical of these hot Jupiters create magnetic forces that act against the circulation of the winds and produce this dissipation that can act as an extra source of heat to inflate them. So there are also the internal currents. They are focused in the dynamo region, where there is this magnetic field that is constantly regenerated. But we are not going to focus on this part, just on the atmospheric part. So in previous works related with this topic, there have been some 3 MHD simulations for global circulation models. So around all the hot Jupiter. But the caveat was that they could not capture the small scales and small turbulences that are created locally in the atmosphere. On the other hand, there were some other papers that tried to study these turbulences, but they did not take into account the magnetic effects. So what did we do in our paper? So in our paper, we tried to study this effect of the atmospheric turbulence, or taking into account the magnetic field, in order to try to quantify the magnetic field and the currents generated there, and afterwards try to determine the amount of ohmic dissipation locally in the atmosphere. So basically, we simulate blocks of hot Jupiters for a small region of the day side, and they were located in a pressure range between approximately 0.01 and 10 bars. So our model, the problem, and the ingredients that we use, I will go quickly because I don't have time. But basically, in our model, we have the equation of state, we have MHD equation, energy equation, and apart from the physical traditional equations, we add a forcing in order to try to mimic the effect of the wind. We add also some small perturbations to create a little bit of heterogeneity in the fluid. We add Newtonian cooling, so in order to prevent that the temperature and the velocity achieves values that are not real and can create a crash in the core. We consider a background perturbation approach, so it means that we have a background component and a perturbed component, and we evolve the perturbed component. And we use Rayleigh scale equations. So in the code, we don't have units, they are dimensionless. So we have to fix some values a posteriori, and it will determine all the units of the different magnitudes that have been evolved in the simulation. So basically, what we did was involve some kind of boxes. Here is just one slide, but basically they are isothermal. They have a physical region, which is in the lower part. We have these physical wind and perturbations, and we have the highest part, which is a damping zone to try to absorb this energy that can go outside of the planet. And regarding the conditions, the boundary conditions, we use periodic conditions for X and Y, and for Z, we use conditions in order to try to ensure the hydrostatic stability and to let the upwards perturbations to dissipate in the upper region. So what did we see in the simulation? So basically, here I'm just going to briefly explain the main results, not the differences among the different parameters. But basically, what we did was to try to explore how the magnetic field and the currents change, taking into account different wind profiles. So, for example, we use three different variations. We also changed the perturbation amplitude, the time correlation, and the Bx treatment inside the equation of the forcing. And one thing that is important to take into account is that we did not use the magnetic diffusivity, the physical magnetic diffusivity. The only diffusivity that we had was numerical. So it means that these simulations are valid as long as the physical magnetic diffusivity is not much larger than the numerical one. So it means for ultra hot Jupiters. So the general behavior that we could observe was this one. In the top panel, you can see different which represent the perturbed density, and they correspond to different timings of the simulation. The main idea here is that there exists perturbation, and there is this perturbation generated in the code that is created at early times, but this perturbation and this unequal representation of the density, if you check, it's basically has a slight dependence. No? So here you have, for example, lower values, and here you have higher values. However, there are also extra contributions, some extra small structures created in the lower region that are due to these extra perturbations that we add to give a little bit more of heterogeneity and at these small scales factors. And apart from that, if we have a look to the magnetic field and the currents, you can see that the magnetic field, the component that has highest value corresponds to the Bx. This is due to the winding effect in the MHD relations, and it has a top value around Z equal to, where we have the shear layer in the wind profile. And well, here you can observe that it's more or less the top. And if we have a look to the cube of the Bx component, you can confirm exactly that here we have the maximum values with some small perturbations here. Apart from that, the other two components are lower. They are approximately orders of magnitude lower than the Bx. There is this curling and twisting effect in the MHD, but they don't dominate. If you have a look to the currents, we have also that the magnetic, so the white component is the dominant one, with a peak also around the shear layer. But here you have this change of scene after the shear layer, and this corresponds to the two sides of the meridional loop in the current around this region of meridional direction. And the other two components are lower, and this is just to the stochastic behavior of the system. So after obtaining these Bx and these currents, what we did was to try to quantify the amount of Ohmic dissipation. So we tried to calculate Qj, which corresponds to the Ohmic dissipation. If there is a dependence on time, on temperature, which is a posteriori depending on the temperature of the flight, and a dependence on J squared. So depending on the J value that we obtain for its simulation, we obtain a different value for the Ohmic dissipation. This is a first calculus, so it's not a final decision. It doesn't answer the question why they are inflated, but it gave us an idea on the amount of deposited heat in the upper radiative layer. It gives us a little bit of information about that the inflation is effective when it's deposited in the inner layers of the adiabac, no? And it gave us a little bit information also about the upper limit of the values that we can reach for these high temperatures of ultra hot. So the main conclusions of the paper were that toroidal fields can be created, and they can reach up to some kilojoules locally. These fields are sustained by the meridional currents. There are these extra magnetic field contributions coming from the smooth perturbations, and we were able to achieve some upper limits for the Ohmic dissipation. But there were some caveats because these simulations were only applicable for ultra hot Jupiters, but not for hot Jupiters. Moreover, we were taking an isothermal profile. It's not a problem, but it's a simplicity. Moreover, we can try to, in the future, to include a better prescription of the conductivity and take into account, for example, the Hall and the ambipolar effects. And we can try to explore a little bit more the possibility of reinforcing, adapting it, and making it more realistic. So we did some of these improvements. And after the paper, we include the diffusivity term to make it applicable to all hot Jupiters, not only ultra hot Jupiters. Moreover, we add GCM profiles. So the wind now it's not an equation, it's obtained from values of pressure, density, temperature, wind velocities from the simulations that Haley Bells, which is a collaborator, gave us. And you can see now that, for example, the temperature is not isothermal anymore, so there is a variation. And the wind profiles are similar to the ones that we were considering, but they vary a little bit. And all these parameters, we are considering them for known exoplanets, so for this list of planets. So now we are doing this work. We have explored so far the boundary conditions for the PX to make them as much realistic as possible, but also taking into account a conservative perspective. We are studying the isothermal and non-isothermal differences, the drag effect on the GCM wind profile, and we are checking these differences created in the different planets as they have different temperature and different diffusivity, magnetic diffusivities. We will also explore 3D simulations. We already did some tests and we confirmed that there are still these small turbulences and small amplifications of the magnetic field. But we want to do some more simulations in order to try to quantify the ohmic dissipation with these updates and see how it changes. On the other hand, we have another project in the group led by Tane, which has been done and we are about to submit it soon. And the idea is to try to answer the same question, but taking into account not the atmospheric ohmic dissipation, but the internal ohmic dissipation. So in this paper, what we have been doing is to try to evolve the code, the planet, but in 1D, and try to check if there is a variation of the parameters of the planet, but basically the radius, because this is the main parameter in which we are interested, but changes, for example, the mass of the planet, the temperature of the planet, and the magnetic length. So here we are considering that the dynamo region, the ohmic dissipation starts at 800 bars approximately, and this dissipation starts just below the RCB, the radiative convective boundary region. So the main results of this project, I'm not going into the detail because I don't have time, but we have checked so far that there's a radial dependence on the temperature equilibrium, which is really strong. There is a dependence on mass, and the dependence on the curvature parameter exists also, but as the curvature parameter decreases, there is an increase in the ohmic heating, and so there is an increase in the radius. So the main idea of the paper is that in order to try to explain inflated radii, these numbers are not enough because the ohmic dissipation of phase is not enough. So we expect the contribution of the atmospheric heat. So it will be a mixed effect between the internal and the atmospheric. So we are still working on this project, and we can do some more updates and improvements. So in the future, we expect to increase the range of pressures of the box that we evolve. We want to analyze more hot Jupiters, more realistic hot Jupiters with real data, to have a better prescription of the conductivity, and to include or to try to include these results that we have inside the GCM profile and the GCM poles, in order that they evolve the field and add the turbulence, which now it's not. So here you have the QR for if you want to have a look to the paper. And yeah, that's all. So thank you.
Thank you for you.
Okay. María said, thank you, Claudia. Congratulations. One question. With all this kind of theoretical work, is it possible to predict with what is the optimal frequency in radio to observe these hot Jupiters? Maybe Simran could answer you this question better. But
The problem is that so far we have not been able to answer to detect the hot Jupiter radiation, but I don't know. Yes, Simran can answer this question better because she's related with the observation and not with the theoretical part.
The thing is that the optimal frequency is magnetic fields. That is like the key point.
Exactly, but the problem is that in some local simulations that we did, so that we can reach kilovolts, but they are local and inside the planet. So
it also like depends on like the initial anything from outside. It's not really clear.
Okay. Okay, so it's not really clear.
Not I have one on myself. We have this right. Fashion. From the
Yes. If I'm not wrong, in our paper, it was around 1%. In our papers, we estimate that the efficiency rate was 2-3%, but in the paper, I think it was around 1%.
they told that it's not enough to
Yes.
so yeah,
No, maybe a combination of internal and external. So an internal dynamo on observation and atmospheric, but we haven't checked the effect of the combination yet.
I mean, it's just we need like 5% on the
I don't.
There are any other questions? If not, let's start Clàudia again. And our next speaker is Michele. But you know him as well. He finished his PhD in Bologna in 2021. If I remember correctly. Yep. And now he's funded at Irradiation here, working with the gravitational waves group. And okay, we will be talking about dynamics of black holes. When you're ready, please go ahead.
Okay, I'm ready. Okay, so thanks. And as Juan Carlos says, I'm going to present this paper. I added this subtitle, computation, which is the follow-up. So we take the second paper. The first one was called theory. Okay. And since we are going to deal with black holes, three body factors of black holes, in order to get there, I would like to try to motivate it a bit, since it's also a kind it was a bit of a formal paper, let's say. So I want to motivate why we are doing all these calculations and see. And to do so, I mean, I think I first have to introduce a bit what is a black hole, certainly. And then we will study a bit by introduce what's one of the main theoretical tools to study this object, which is black hole perturbation theory. And then in the second part, I will introduce this quarterly Lewis symmetries, which is what we found in this paper of black hole perturbation and how we use them to calculate physical quantities. So this is the idea. And so to start with, what's a black hole? For me, let's say. So a black hole is going to be a general relativistic black hole. So the general relativity prediction, which says that black holes are regions of space-time which are causally disconnected with the exterior. So basically, the only thing you can experience is the outside region. But maybe a more intuitive understanding can be given in the parallelism that was introduced by Einstein in general relativity between gravitational interaction and space-time curvature, right? Which is depicted a bit in this horrible picture. But I think you can understand that, and it gives the impression that it's not about the mass, no? The space-time deformation, which is parallel to gravitation, is not directly related to the mass, but more to the component, right? So this is more compact stars deform the space-time more. And black holes are the extreme situation of this. So they are the extreme deformation of space-time where this well, right, this tube goes up to infinity. And I mean, outside, right, far away, we don't experience anything different, right? In this, they're almost flat, all of them. But the more we get closer to the object, the more we feel the curvature it's generating. And in order to understand a bit more, maybe I hope when we get what happens when we get really close, I show this diagram, which is radius, right, on the horizontal axis, and time, basically. So this line here is describing the surface of a shrinking star, right? This is the ball, I'm in one level. And this is the interior. And so what this picture shows is a bit tutorial, but you can show that this is what happens with math, right? Is that the more you get, the more the surface of the star shrinks, the longer light rays takes to reach an external observer. So this means that up to the point, to the extreme point in which I am at the horizon, common with the laser on the surface, when the star gets to the horizon, then even the laser, so not even light rays, can escape. They will remain trapped in this position, right? And if you get inside, they will just enter. So this is a big qualitative prediction. So we have the horizon, which is called like this because nothing can escape from it. So no event is seen from the outside. And then the inevitable thing that this picture is showing is that if this was a star, right, it has a mass is shrinking. So the black hole is thought to possess a future central singularity. So it's not that it's a ball with a central singularity, but it will inevitably evolve according to GR to a singularity. And this is also one of the main motivations to try to break this black hole paradigm, which we hope to test with gravitational waves, for example, which can be encoded in this theorem. It's called Buchdahl theorem, but basically it boils down to saying that these predictions are true if we have GR and ordinary method. So it also gives us the recipe to break this thing. So considering modified theories of GR and seeing what are the consequences on compact objects, or changing the method size. So you can play, and this led to the review on the so-called exotic compact objects, which there are many. Not all of them are fully consistent, but there are many. And this is just to motivate a bit also the study and the importance of digging deeper into the understanding of black hole perturbation theory, which is essentially the idea that in order to learn something about these objects, either GR black holes or exotic objects, one of the best tools is to perturb them and see how they react, right? So this is one of the most powerful things that we have from the theoretical point of view and can describe a number of phenomena like scattering of particles and waves to black holes, right? So I send packets, which has as a particular case the Hawking radiation. I will say something more later. The other case is the typical binary black hole system, right? So, well, of course, black hole perturbation is not being able to capture the whole thing, but just the ring down part. So, this is the typical binary system. So we have, which can be divided as usually in three parts, right? We have the spiral, the merger, and the ring down. The spiral is basically described by this oscillation in post-Newtonian physics. We have the merger, short part, where you cannot escape by using numerical relativity, basically. There's kind of linearity from fields and everything is contributing. And then there's the ring down part, which instead is composed by this deformed black hole. Actually, I have the video, which I think helps a bit. Not seeing it all because there's no time, but here you see the video. This is a simulation of a system of binary black holes, which in spiral, this is the spiral part, they are still far away. And this is the deformation, right? The cone that we were showing before. So we have the singularities, and we see that here they start merging. So the space-time is really chaotic and really deformed. There's no way we can do something analytically for now. And here is where they start merging and form one black hole, right? And from here, let's say black hole perturbation starts to be useful. Describe this part where I have one black hole, which is the form, right? And is relaxing down, emitting what are called these quasi-normal modes, right? Which are the typical complex modes. Yeah. This bumps up. I think that this is just the deformation. I mean, that's a really, I wouldn't trust fully, I don't know if I was mentioning, but I wouldn't trust fully this pictorial thing in the merger, in the sense that we don't have much information in that really tiny, I mean, the merger is happening in a really tiny region. Then you can imagine that maybe we reach some super high precision and we can make a super zoom on this region, and maybe there we see something, but in the end, it's not what we have, right? So we are not seeing details of what's really happening there, I would say. Okay. Well, these peaks in the simulation when the two things merge, I think it's a numerical. Yeah. Yeah, it's not too physical, let's say, I would say. Yeah, but it's not too informative. And yeah, and in this ring down part, so we have this relaxation, no? So quasi-normal modes, you call them, which are complex modes. So they have an exponential damping, they have an oscillation part and an exponential damping. And this kind of modes emerge in black hole perturbation theory. That's the natural arena where you can define them, as we will see a bit. And they trigger this so-called black hole spectroscopy. So in the line of atomic spectroscopy, right? They should be considered as the line elements of defining a black hole. There are some problems, I would say, and I think we are trying to address exactly these problems, because it has been seen that you have fundamental levels and then you have excited levels, right? So higher order quasi-normal modes. And there are some results, some important results recently, that this may not be stable. So they may not be so informative. So how is this black hole spectroscopy really informative? But maybe I'll say something more later. And then other kind of sources which are well described by perturbation theory are gravitational wave system with sources, with perturbative sources. Like, for example, EMRIS, extreme mass ratio in spirals, where you have a small object, a small black hole, spiraling around a big one. And that is where perturbation theory is working, because the small black hole is the perturbation to the other. And you can really follow these calculations. Now, also, again, to try to motivate these theoretical works, I mean, all these things are supposed to be observed by future gravitational wave detectors, like LISA. This is one of the science cases for LISA, for example, quasi-normal modes in Einstein telescope and LISA again are supposed to be detected with quite high precision. So the thing is, we're going to have ideally very precise data, but in order to exploit them and extract physics from them, we need really precise models, right? Otherwise, if we glue up a bad model on good data, we are not learning too much, right? So this is why I think it's important to enter really the theory of this black hole perturbation. But there's still things to be understood, I think, and that it's worth digging. And to do so, we need to introduce some structure, some mathematics, and so the starting point are, of course, we are studying perturbed black hole. So the starting point are perturbed Einstein equation. So Einstein equation plus perturbation. So these are 10 partial nonlinear coupled differential equations. So involved, but it turns out that you can, well, okay, I have to accelerate a bit, but you can mesh them in strange ways so that you cast them in the form of a wave equation, right? This is just a typical wave equation in flat space, if you want, where you have a wave function, psi, which only depends on these perturbations, and a potential, which instead only depends on the background. So this is the actual response of your black hole to anything which moves in his spacetime, right? So it's not true that you draw something and it just enters. You have to have enough energy to overcome this barrier, right? Which is encoding a lot of physics. I mean, it's the way in which the black hole responds to something external. And so this is the physics part of the potential. Regarding the master function, so the psi can also be associated, I mean, looks like a mathematical combination of things, but it turns out that it's related to the strain of the signal, right? This is the strain, if you want, the H signal. And this you can find it in the ring down, of course, or if you are in MRIs throughout, I mean, for the whole process. But this encodes for the gravitational degrees of freedom. They encode the signal, this wave function in some way, and as well as the luminosities, which are the emissions of energy and angular momentum. So we are going to focus in these last 5 minutes. I try to jump on the paper to scattering, black hole scattering. So we have this barrier outside. We can throw things. I just learned 2 minutes, huh? For me, it's fine. Okay, so we are throwing things to the black hole, and we are seeing how these things react, right? So we can either throw from plus infinity, let's say, and see how much of it passes and how much not. That's a typical situation. Or this I depicted here, for example, is the Hawking case, right? There's something coming from the horizon, the incident wave. Part of it is transmitted, part is reflected, right? Typical. It becomes a quantum mechanical problem, basically, which you can define in this way, the typical way. This is the formula of what I just said. From minus infinity, I send something. At minus infinity, I have something reflected. At plus infinity, I have what function, right? And all these things are encoded in this gray body factor, which are telling me how much is reflected and how much is transmitted. And the quasi-normal modes can also be seen in this setup from mathematical point of view. They are the zeros of this object, the transmission of the inverse transmission. You can define it this way operationally, which correspond actually to killing the incident part. So they are free oscillation, right? It's like the trick is like this, right? I'm not sending anything. I have just things outgoing, right? So this is the idea of quasi-normal modes, just free oscillation of these things. There's nothing from the outside. And so what we do, I think it's important to study symmetries of these things. I mean, we want to study the theoretical part, and symmetries are always from the theory a kind of guide. They give you conserved quantities and they give you a lot of handle and understanding on your theory and your equations. And so in a previous paper, we found some symmetries of this black hole perturbation equation associated to the Corteville-Debye equation. Nothing to do now. I'm jumping to fluid physics if you want, because this equation is a nonlinear equation for this function, which describes, well, first, there are many systems in physics, but the first one was to describe shallow waves in shallow water, right? And so this is, for example, it has been seen, like there's this history, but you can see that you can generate solitons, right, in shallow water. So you have shallow waters. There's a way to generate these solitons, which are waves which travel right, unchanged. They never die. They are conservative throughout the whole. There are videos. This is a picture from a video. You can do it, and you can see that this wave is just never vanishing, never. Of course. And so the curious thing, I mean, that to try to make a parallel is, if you notice this diagram of a soliton reminds quite a lot the potential of the black hole, right? That we showed before. This thing here. And actually, what we found is that if we identify this potential, this soliton, with the potential, and deform our equation following this equation, it's a bit technical, this thing, but we are using this system to deform our system, let's say, we realize that these deformations leaves all the physics that I just described before. So quasi-normal modes, scattering, all these things are invariant. So I can deform it as much as I want in this way, and the physics will not change. So this is a symmetry of my equation. And it comes, as every symmetry, associated with some conserved quantities, which are these Kirby integrals, right? They are just numbers, if you want, constants. Actually, they are inversely proportional to the mass of the black hole. Yeah, right. And it turns out that, I mean, as usual, when you have symmetries, you have conserved quantities, and then you can go back and express usually things in terms of your conserved quantities, right? That's why they are powerful, they are useful. And that's what we try to do in what we did actually in this paper. And we realized that working it out, you can find that the gray body factors of the black hole can be entirely expressed in terms of these constants. So these constants are associated to these symmetries that we found, right? And it turns out that the way in which they are related is through a moment problem, which we call black hole moment problem. The moment problem is that, I mean, it's a typical problem in mathematics, statistics, most places, right? You have a distribution, and you can calculate its moment. It could be the mean, the variance, or a statistical distribution, also. But in this case, the distribution depends on the gray body factor. And the moments are these conserved quantities. And so we were able to invert this relation. Actually, in the first paper, what we did is, when you have this problem, and to be formal, you have to first show that you can solve it, that your solution is unique, and that you can construct your solution, right? In the first paper, we were able to do the first two steps. So show that there is a solution. This relation between this constant of these symmetries is real. We show that it's unique, and you can show it in these two plots. They depend on the moments. There are conditions on the growth of this moment, on the behavior, mathematical behavior of these objects, of this KdV integral. And then in the third one, we managed to build this solution. This is the typical plot of a gray body factor, right? So if I imagine I'm drawing something, this is the transmission coefficient, right? So if I have zero, if I draw something at zero energy, it will not pass, right? So there's no transmission. Everything will be reflected, so zero. But if I throw it at higher and higher energy, everything will pass, right? So it will be easy for this thing I'm throwing to overcome the barrier. And so if this one goes to 1, because everything will pass and nothing will be reflected, right? Just understand this shape. And well, these are just the plots. I mean, it's hard to see it because you cannot distinguish our approximation from the true value. This is the post-stellar case, let's say, and this is the case of the potential of the black hole. So as we see that the approximation is very good, and I think that it's good to have something which comes from symmetry. I finish. And yeah, I think that symmetry gives you a nice sample, a nice understanding, and they encode naturally, you know, what's the physics of your system. It's like you are throwing away what's irrelevant and you are keeping what's relevant to describe your system. And I think that this is what we try to do here, and to identify these strange quantities which seem to have nothing to do, but in the end they enter in this description. And we have many outlooks, many things we want to do. Let's say the first one is, of course, get to quasi-normal modes. So we are very confident. I can give you strong motivation that quasi-normal modes can also be related to these quantities, to this KdV integral. We are not being able to find this relation because, as I said, these quasi-normal modes are slippery quantities. You define them, but then they are unstable. So it's not too easy to define them rigorously and properly, and then related to symmetry. But I think that this could be a powerful tool also to address this instability of quasi-normal modes that I mentioned before. And then I think that, I mean, first, this approach is really systematic. We have control in each step, let's say. So we can imagine to extend it to alternative theories and study, as I said before, different kind of theories, objects. It's easy to include phenomenological deviations in these things. Usually the way to study ecos, exotic compact objects, is to You say that it's for the logarithm. It looks to you like an entropy.
I'm just saying that if there's any connection.
Well, I don't know it. If it's there, I don't know. It may be. I mean, I should think about it. I mean, in the end, there is this thermodynamic relation in black holes. I'm trying to think. But then entropy is related to the surface area of the black hole and these things. Yeah, I mean, in the end, I think that these things are showing that there are some universal, right? I mean, when you go into the pure theory, I think that you start seeing universal structures, right? In what you have there. And I think it's non-trivial and it's worth, recognizing them. I mean, all these questions, I think, all the connections. In doing these things, we had so many connections with so many fields of physics, because when you go mathematical, I think that then you start seeing, I don't know, ramifications.
So you reshape inflation equation to the form of equations of a function, right? And you tell us something about this potential? Did you put in here?
I'm not reshaping. I mean, I don't know if I understood properly, but I'm not reshaping. I'm still using a wave equation, right? Yeah. But what I'm doing is I'm deforming it.
No, but my question is, what is this V?
The V is my potential. So V for me is the black hole potential. It's this thing here, where I took out. How does it look?
Yeah.
This is the residual potential. I mean, I can write it down. It's powers of R, of 1 over R. So it's a potential. When here, if
how it depends on the constants of your problem.
Yeah, it has a centrifugal barrier.
No, on the constants.
On the perturbations.
Yeah. Yeah, it has the metric function. Then you have the centrifugal barrier, so L plus 1 over R squared, and then another term depending on the mass of the black hole.